In this video, we're going to dive deeper into how we can calculate summary statistics. Here's an example we looked at before. We used the summarize function to calculate the mean, the minimum, and the maximum of the age column. The summarize function is typically what we are going to use to calculate summary statistics, and we can then supply these aggregating functions inside it, such as the mean function or the min function or the max function, to convert an entire column of data down to just a single number that summarizes that entire column. So a schematic of how this works is on the left here, we have our original data set with n rows and p columns, and we can convert columns into single numbers in the output. The output of the summarize function is also a data frame, but it's one where each column is a summary statistic that we've calculated. So let's take a look at the syntax of the summarize function. The first argument is going to be the data frame. Well, here we're piping in the data frame with the pipe operator, so we don't actually write the data set within the summarize function. Then the remaining arguments of the summarize function are the aggregating functions that we're going to use to calculate the summary statistics that we want. We have this n function, we have this mean function. And the other thing that we can do is we can say that some value equals that aggregating function. The value on the left-hand side of the equals operator will be the name of the new column for that summarize function, for that summary statistic. So what does this example look like? Well, the n function, it doesn't take any arguments, and what it does is it calculates the total number of rows in the input data frame. So the reason we don't need an argument is because it doesn't matter what column we were to look at, all of the columns have the same number of rows. So we don't need to specify a column. And the output we get is that there are 920 rows. Now, one thing you'll note is that because we didn't specify a name of this new column in the output of summarize, it's just called it the entire function that we used to calculate that summary statistic. This is not typically what you want. So what we usually want to do is what we've done with the mean function here, where we specify the new column name that we want for this. So there are quite a few different functions that we can use to perform these data aggregations within Summarize. So we already saw the n function that counts up the number of rows. We can also add up the values in each cell in a column. And for that we'd use the sum function, and within that we would write the name of the column that we want to add up. To calculate the range, we can use the min and max functions. And then there are a variety of different functions we can use to calculate statistical values. So different values that calculate the center of a variable's distribution or its average, right? So the mean function or the median function. And then other functions that calculate its spread. So SD, which calculates what's called the standard deviation, as well as the min and max functions that we just mentioned. We can also combine the summarize function with another function called group by. When we do this, we use the group by function before the summarize function. And so we pipe our input data frame to group by, and then we pipe the output of group by onto summarize. And within group by, we supply a variable that we wish to group by. So here we're grouping by the diagnosis column. And typically we want to group by a categorical variable. And the diagnosis column is categorical. It contains two values, whether a patient is disease-free or whether that patient has heart disease. The effect this has when we get to the summarize function is that summarize then calculates its summary statistics separately within each group. So we get a group of all the patients or rows of the data frame where the diagnosis column equals disease-free. And we can see that the end function says, oh, there are now 411 rows in the category. Similarly, there are 509 rows in the heart disease category. And then we get separate means and medians for both of those categories as well. So this allows us to look at the covariation between different variables. We can look at the covariation between diagnosis and the age column. And we can ask ourselves, what kind of insights can we draw? So we could say, for example, is there a difference in the mean age between patients in the data set who are disease-free and those who have heart disease? Now, one problem can happen when we have missing data in a column. In a data frame, missing data is typically recorded using this value called NA. And if there's even a single NA in a column, like there is in the cholesterol column, then the output of a lot of summary statistic functions will also be an NA. Because what the function says is, well, if I have a bunch of numbers but also an NA, then I can't calculate an average of all of those values because I don't know how to handle the missing values. What we have to say if we want to get the summary statistic for all the non-missing values is to explicitly tell these summary statistic functions to ignore the NAs. And we do that by supplying this na.rm argument, which we set to be true. When we do that, these functions, like the mean function, ignore the NAs and calculate the mean of the remaining values. We can also do more complex calculations within the summarize function. So one thing we can do is turn a column into a logical vector, a vector of trues and falses. So in this first example, we're comparing to see whether column 1 is greater than 10. And what this bit of code inside the sum function will do is it will convert column 1, which is presumably a column of numbers, into a column of trues and falses. And then the sum function will add up the trues and falses. And that relies on the fact that true is equal to 1 and false is regarded as being equal to 0. So it will add up the number of cases where this Boolean comparison is true. Similarly, in this second example, we're using a function called is.na, which checks to see whether a value is an NA value, a missing value. And by supplying this column within the is.na function, we go through every value in column 2 and check to see if it's NA or not. And the result will be a vector of trues and falses again. And then the sum function adds that up. And so it's going to add up a 1 for any output of is.na that's true, right? So any output where there was a missing value. And it will add a 0 for any case where that output was false, i.e. where there wasn't missing data. Well, obviously, if we add up zeros, then that doesn't contribute to our sum. And so what this code would effectively do is just count up the number of cases of missing data in this column. The other thing we can do with the summarize function is when we've calculated one summary statistic, we can use that summary statistic in another summary statistic calculation within the same summarize function. So here's some examples of this where we can analyze the missing data in more detail. So we have the code we looked at before to calculate the mean of the cholesterol column. And we're also calculating the number of missing values in the cholesterol column using the code that we had from the last slide, summing up the logical vector that is produced by the is.na function. We can see there are 30 missing values in the cholesterol column. This next summary statistic then calculates the fraction of values that are missing by dividing n missing by the n function. Well, we already know the n function calculates the total number of rows in the data frame, and n missing is the number of missing values that we calculated as the previous summary statistic. So we're using the previous summary statistic to calculate this frac missing summary statistic. And then we're doing a similar thing here to convert the fraction of missing values into a percentage. So all we're doing is multiplying frac missing by 100 to get the result that there are 3.2% of values that are missing in this cholesterol column. So we can do some pretty cool stuff with the summarize function to calculate different summary statistics, but you should be aware that there are some limitations. So here's a famous example of the kinds of problems we can encounter using a data set called Anscombe's quartet, because it was created by a statistician called Anscombe. And what he created was 4 imaginary data sets, which you can see here on the graph in the left. And each one of these clearly has quite a different pattern, right? We have this sort of linear relationship here in this first plot, a curved relationship here in this second plot, a very precise linear relationship here in this third plot, but with one outlier, and here just a vertical series of points, again with one outlier. So you would look at the graphs here and you would think, oh, these are very different patterns. But if you were actually to calculate the mean and the standard deviation of each of these 4 data sets, what you would find is that all the numbers are the same, even though the data clearly has very different patterns. And similarly, for the standard deviation, these are essentially the same for both the X and Y columns for each of the 4 data sets. And so this highlights a problem with summary statistics, which is that the numbers can sometimes obscure variation within the data that we might be able to see if we were to plot the data in a graph. So we never want to use summary statistics by themselves. We always want to explore data sets with visualizations as well.